And we did a bunch of samples and we tried to find the probability of that. Well, we're going to do the actual hypothesis test, start to finish with it, so that you can see how it's run. We'll rerun it Monday, so you've got 2 trials under your belt, and you'll see it's very repetitive of what we've done before. Okay, so we're going to do that same significance test. It's not from 6-6. We numbers ours differently. It was from 9-1. Okay. So it was a free throw rate. So a rate is a proportion. So I would use P. And my claim was that it's 80%. I'm an 80% shooter. But if you remember, when I shot 50 shots, how many did I make? Anybody remember? 34 out of 50. No, 32 out of 50. So it was 64%, right? Which is obviously less than 80%. So we think it's less than 80%, or you guys think it's less than 80%. So this is our evidence right here, right? So our job is to test the evidence and see how strong it is. Can we conclude that I'm exaggerating from this evidence? Is it unusual enough? Do you remember what we decided Monday? Remember it was like a 0% chance of happening, and you're like, you're lying. Remember that? Okay. So each class found a different p-value. So we're going to actually calculate the true p-value today, but we have to be able to use the normal distribution. How do we test for a normal distribution with proportions? Do you remember? You did this in confidence intervals.
Yes.
What did we use?
It's the large counts thing, where it's like NP
Yep.
is greater.
Yep. NP has to be greater than or equal to 10. N times 1 minus P has to be greater than or equal to 10. Remember, that's the large counts. It only works for proportions. Now, do we know what N is? 50. What did we use for P here?
You use the null.
We're going to use the null value for P. When we did confidence intervals, we had to use P hat because that's all we had. But now we have a null that we are assuming is true. So we're going to use 0.8. And that gives me 40. That's greater than 10. And then I do the complement is 0.2. And that's equal to 10, so it works out. So we can show that this is approximately normal. So we know we're good to use norm CDF eventually. We've proven we can. What other conditions do we need to check? Random. And independence, or you can call it the 10% test, right? Now, when you do random, was it stated, or was it, did you experience random? Was it random that I threw free throws? Yeah. Yes, okay. So you can just say free throws are random. Now, I will warn you, on the test, last test, when you checked the random condition, I saw some of this. Guess how much credit that's going to get? None. They do not accept that on the AP test. So I'm telling you now, I won't either, okay? You got to give me something, either stated, you can say stated, you can say the sample size, you can say given in the question, something to the effect that you've processed that, not just a nice little check mark, okay? Right? Okay, 10% condition, okay. So is 50 less than 10% of all free throws?
Yeah.
We're going to make that assumption that that's reasonable. So make sure you put your 10% in population context. Now that the conditions have been met, find the mean and the standard deviation of that sampling distribution. The mean of all the p-hats, if we did every possible sample of 50, do you remember what the center of it would be? Just the, well, in this case, it's the true proportion, right? Whatever the null value is, so it's just p. So in this context, it's 80%. The standard deviation of all the p-hats, this is straight off your chart. We use that. That's going to give us the standard deviation. 0.8, 0.2 over 50. Take a big fat square root of that. What's going on out there? Okay, this gives me 0.0032. There's my standard deviation. Okay. Now, we know the mean, so when we draw our normal curve, we know the center of it is going to be this 80%. Yeah.
Wait, did you not take the square root?
Oh, you're right. I wrote down the wrong answer.
I can't believe this.
You can't believe I made a mistake? Are you kidding? Ryan, you've known me way too long.
0.056.
Yes, I looked at the wrong one on my calculator. My apologies. 0.0566. Thank you. Yeah, make sure you take the square root. What I did. Now, the simulation is asking us to take the center, the 0.8, and subtract 0.0566, or add it 3 times, subtract it 3 times. That's really tedious. We're not going to do that. Okay? What we need to understand is, where did our sample fall relative to the 0.8? Is it less than or greater than? It's less than. So I'm going to just mark it. Oops. I'm going to mark it over here, 0.64. And if it's a less than, it's a left-tailed test. Remember that verbiage? That's as fancy as your chart or your drawings need to be. You don't have to get super detailed. Now you can calculate the z-score, which would tell you exactly how many standard deviations below the mean, but you don't have to. At this point, we want to find the area under the curve that we've shaded. So how do we find area under the curve? Not inverse norm. That's when we're given the area. You're on the right track. So what's the reverse of that? Norm CDF. Norm CDF. So let's go back to norm CDF. What would the lower boundary be? Negative big number, right? Upper boundary? 0.64. The mean? 0.8. And the standard deviation? 0.0566, what we calculated, right? Okay, now, when I put that in my calculator, I get an area of 0.0024. So now, to draw our conclusion, we have to know the alpha value. Now, did it tell us an alpha value? I don't see one. So if they don't tell you, the default is that good old 5%, 0.05, okay? If they don't indicate otherwise, that's what we go with. So when we draw a conclusion, the very first thing we do is talk about our p-value. So we'll say since 0.0024, is that greater than or less than 0.05? Okay, since it's less than, what happens when it's less? When p is low, we reject the null. All right, that's the decision part, but we need to draw the conclusion. What does that mean? If I think back to my null and alternative, I've rejected this. That means I have evidence of this, that I can say they're guilty, okay? If guilty was the alternative. But I can say that the true free throw rate is less than 80%. That's what we're saying. So we put it in context and we write it out. So you would say, we have convincing evidence that Dobbs's free throw rate is less than 80%. We can't say for sure that it is 80%, or yeah, we can't say for sure what it is, but we know it's less than 80%. Okay? So want to indicate, make sure, what do we have evidence of? Whatever you say in here is going to reflect the alternative hypothesis right there. Even if we fail to reject and we do not have evidence, what do we not have evidence of? The alternative. All right? This will become very habitual. I just want to make sure you're referencing the right hypothesis. Okay? Questions so far? Do you see how some of this is all coming together? All these pieces are falling into place? All right, let's look at the back and summarize some things. Okay, random. Our sample has to be random. Do you remember why it has to be random?
So it applies to the population?
Yeah, so the results apply to the general population. Good. If we don't check for random, it won't apply. 10% condition. We have to do that because of our standard deviation stuff. But to show it, we show the sample is less than 10% of the population. But you always want to make sure you put that in context. And then normal large counts only applies to proportions, but we've studied it before. N times P is greater than or equal to 10. N times 1 minus P is greater than or equal to 10. Both have to be true, which 99% sure it's going to always be true. I've never seen anything not pass that. But you have to prove it, all right?
With 99% confidence?
I am 99% confident you're never going to see anything that doesn't pass the test on an AP test. Okay? So you're looking at you using stats humor. That's a good job. All right. When you do the standardized test, do you remember when we did the intervals, you had to name the procedure? You had to say 1 proportion Z interval,
Yeah.
1 proportion T interval. Here's our procedure. It's a 1 proportion Z test. It's not an interval. A result is not a test. Or it's not an interval. It's a test. We test a hypothesis. So this is our third procedure in our tool belt, basically. All right. Picture, when you draw your picture, you're going to put the null value straight down the center, whatever that is, and you're going to shade either 1 tail, 2 tails, or 1 or 2 tails. You can't do 3. All right, shade it, and then you're going to need to know your mean. That's going to be the null value, right? You're going to need to show your work for calculating the standard deviation somewhere. And then I know what you're going to do. You're going to use norm CDF instead of a z-score formula, right? Let's just be honest. You're going to use norm CDF to find that. Now, when is a result statistically significant and has convincing evidence of the alternative? That is when the p is lower than the alpha. Or that is when we reject the null hypothesis. Those results are considered statistically significant and we have convincing evidence of the alternative. Okie doke. All right, let's try one out here. Sharon claims that 90% of her students can identify the smell of a skunk. She carries out a study to test the theory. She selects a random sample of 100 students and asks them to take a whiff from a bag that is filled with skunk smell. Don't ask me how she did that. I don't know. So many questions, right? Okay, she found that 84 students were able to correctly identify the smell as that of a skunk. She'd like to know if these data provide convincing evidence that less than 90% of students can identify the smell of skunk. All right, use alpha 0.05. All right, state the hypothesis for performing the test, define the parameter. All right, so the null, is it proportions or means we're dealing with here? Proportions. All right, what is the claim? Well, she thinks it's less than, but the claim is that it's 90%, right? Sometimes it's the alternative that jumps out to you more often, so I get that. So if that's less than, that means the null could be greater than or equal to, right? Now I need to define P. It's the proportion of students who can correctly identify the skunk smell. Now it says, explain why the sample data gives us evidence for the alternative. Well, what is the sample data? All right. P hat, she asked 100 students. How many of the 100? 84. So that's 0.84. How does that prove, how is that evidence of the alternative? Because it's less than, which is less than 90 degrees. That's our evidence. Our job is to mathematically test the evidence to find out, is it strong enough? All right. Now we check the conditions for performing the significance test. So let's do this. Was the sample random? Yes, it was stated. I like to put the sample size there just for reference because I'll need it in a second. 10%. So the question is 100 less than 10% of all students? There's always that chance, right? But we're going to assume it's okay. We're going to assume it's okay. All right, normal. In this question, since it's proportions, I have to use large counts. So I'm going to say 100 times 0.84. Well, that's definitely 84. That's greater. Oh, not 0.84, is it? What is it?
No, it's 90.
Sorry. You should have caught me. 90, the null value. Use the null value here. That's greater than 10. That's equal to 10, so it passes. So we know it's normal. Now, calculate the standardized test statistic. That is code for z-score. You don't have to do that to get your p-value, but you can. The ultimate goal is to get the p-value. And to get that p-value, you're going to use your norm CDF. All right, so here's where, as far as showing work, you're going to show me the curve. Down the center is the null value. And then I'm going to put in the 0.84. That's lower than 90%, so I'm going to shade less than. And then I'm going to use my norm CDF to find that area for me. So norm CDF. The lower boundary would be negative big number, right? What would my upper boundary be? 0.84. The mean? 0.9. Standard deviation, do we have that yet? We got to find it, don't we? All right, let's sidebar. Let's do that. See if I can remember to take the square root this time. Okay, yeah, this one comes out nice and neat. 0.03. Alrighty. When I do all that, I'm going to get my p-value. Comes out to be, that area is 0.0228. Okay, we'll make a decision, draw a conclusion. So we always start it with since 0.0228. How does that compare to our alpha of 0.05? That's less than. If it's low, we what? Reject the null. If we reject, do we have convincing evidence of the alternative? Yeah, yes. We have convincing evidence that, and here's where I put in my context. If you need to go back to the stem of the question to remember what it was, then do that. That the proportion of students who can correctly identify the skunk smell is less than 0.9. Yes, sir.
So is the z-score the same thing as p-value?
It's not. If I did the z-score, I'll show you what it looks like. See if you recall this. The z-score would have been 0.84 minus the null, and then over the 0.03. Let's see what I get here. So it would be -2. And then when I did norm CDF, my lower boundary would have been -1,000, whatever. Upper boundary would be -2. The mu would be 0, and the sigma would be 1 because I standardized it. I would end up with the same p-value though. Does that make sense? So the z-score requires this because it's converting your observation into how many standard deviations above or below center was it. All right. Other questions?
So we'll never need to use z-score?
I wouldn't say never. You may see it here and there, but if it's just asking you for p-value, you don't have to. You can just go straight to norm CDF. Sometimes they'll do z-score stuff for you in multiple choice, and we'll review that when we get closer because it's not hard to calculate. You just have to remember what it was. All right? Fair enough?
I guess.
You guess. Why are you doubting all of a sudden?